Hello, this is Autonomous Navigation Lab of Ina University. We will present the autonomous driving system we developed. First, we will introduce our project and explain contest missions and our solutions to them. Next, detail algorithms at each sensor. Finally, present the result and conclusion our team's future work. Our project is to embody an autonomous driving system. This project includes object avoidance, parking, delivery, and overall driving like lane keeping and traffic sign compliance. After, we will introduce the method of how to resolve. First, we will introduce a preliminary match, track driving. This mission is to drive lower on track. We mainly use camera and LiDAR to drive in this track. About the main match. First, path tracking. This mission is to keep lane to drive in proper scenarios, including right turn, left turn, and traffic sign compliance. Next, introduction of parking and delivery mission. Parking mission consists of exploring the parking space and parking. The delivery mission consists of recognizing the delivery area and parking in that area. And last, collision avoidance. We will avoid obstacles by generating a local path when recognizing any obstacles. From now, we will introduce details of development. GPS sampling time is not short but accurate. On the contrary, IMU sampling time is short but has accumulated error, so we integrate each other to complement. Accurate state information can be obtained through GPS IMU integration using the Kalman filter. Kalman filter is applied using 15 state variables including position, speed, and angle value. For vision system, to improve the stability of the deep learning model, we use a machine vision camera and specify parameters. As we separated the image reading and detector process, so we use an image queue to prevent the delay of our processes, and separated detectors into lane detection and object detection to each ROS node. To train YOLO V5, we used AI Hub dataset, so we can procure labeled 8,000 images per label. This is about the main development of the LiDAR sensor. To improve the ground removal, we tried the normal vector extraction and purification process and extraction area limitation. Clustering for object detection depends on the point interval, so we developed an algorithm that can keep it constant to cope with the point interval change depending on the distance. Next is the calibration process of the camera and LiDAR. Since the coordinate system of the camera and the LiDAR are different, it is necessary to match them. Obtain intrinsic matrix to correct distortion of the camera itself, and then obtain extrinsic matrix about location difference between the sensors. The product of two matrices is the calibration matrix. It converts the world coordinate of LiDAR into a 2D coordinate. Now the LiDAR bounding box is projected onto the camera image. In this slide, it explains algorithms that generate and track path. First, we obtain alpha from waypoints that based on look-ahead distance and heading, then calculate steering angle to control platform. Next is the collision avoidance algorithm. Obtain the safe distance to create a circle. We designate the intersection with the existing path as first point and last point. Next, specify the vectors looking at the first point and the last point from the center of the object as V1 and V2 to find theta between them. This is how we implemented an algorithm that tracks the path by converting global path to local path as shown. The whole process is summarized in a single chart. The result of camera, as we can see, UV5 can classify sedan and SUV and LED yellow-green sign, or LiDAR. Through the sampling process described above, the point density that decreases by distance can be maintained at a certain level. Excessive EPS to ensure clustering performance makes runtime high, so the developed sampling algorithm can maintain proper EPS and improve runtime. We are going to improve the runtime deviation as well. We can get sensor fusion bounding box using calibrated LiDAR and camera bounding boxes. The result of GPS INS integration using Kalman filter, yaw error occurred within 1 degree, low pitch error occurred in 2 degree, and speed error occurred within 0.5 millisecond. During summer vacation, we are going to put better results in our control system. In the video, we can see we avoid rubber cones well. Finally, we will present our future work. In GPS, we will apply GPS IMU integration to a platform and develop the sensor integration with. In the camera code, to protect against using many resources in the image queue, we planning to use a double buffer. In LiDAR, we will develop localization, tracking process, and code optimization for stable object management and sampling time improvement. For control and path planning, the goal is to develop code at preliminary, implement fail-safe code, optimize MATLAB code, and eventually convert the MATLAB code to C++ at ROS. There are synchronization, tracking, and duplication problems of camera and LiDAR input data, and we will improve them. Furthermore, we are planning to develop early fusion. Thank you for listening.